In this session, we'll study the delta-delta connection. This particular delta-delta connection is useful when neither primary or secondary requires a neutral and voltage are low at moderate. Because as such there is no start point in the case of delta-delta connection, therefore you won't get neutral on either the primary side or a secondary side. In such applications, you are using a delta-delta connection and the voltages are low and the moderate range. Both the connections are the delta-delta in the primary and secondary. Therefore, the ratio of line voltages on primary and secondary side is equal to the transformer ratio of the transformer. Because both are having the same connection, therefore the line voltage is equal to phase voltage in the case of delta-delta connection. Both primary and secondary are delta-delta. Therefore, the transformation ratio is same as the voltage ratio, that is the line voltage ratio is also the same as the transformation ratio. This connection can be used even for unbalanced loading, that is, it is capable of handling the unbalanced loading also. Then another main advantage of this type of connection is that even one of the transformer disabled or fault, in that case system can be continued to operate in an open delta connection but with reduced available capacity. Means if any one of the transformer in the bank is not operative or disabled or it is a fault, then the system can be operated with the two transformer with the reduced capacity. Then this is a delta-delta connections we have out here. In this case, we have both the primary and the secondary have got the delta-delta connection. Here, this connection, what I am considering here is, it is a zero phase shift the connection. Zero phase shift the connection. I have got a three transformer, single phase transformer. Both primary and secondary they are connected in the delta. That is, A1 is connected to B2 and B1 is connected to C2, C1 is connected to A2. Similarly, in the secondary side also, A1 is connected to B2, B1 is connected to C2, C1 is connected to A2. That is, this is how we are getting the connection, that is primary ABC. Then here also this A1 B2 is connected, B1 C2 is connected, C1 A2 is connected. Then you have got a ABC of the secondary here. Now if you are drawing the vector diagram, that is, I am considering here the ratio of the transformer from the primary to secondary 10:1. Suppose if I am taking the phase voltage of each, the transformer is 100 volts each, but it is a delta connection. In this case, both the phase voltage and the line voltages are the same. And the ratio is 10:1. If there is 100 volts here, then there is a reduced voltage you are getting across the secondary, that is the ratio is 10:1. If it is 100 in the secondary side, you are getting the 10 volts. However, at the same time, if you look into the line voltage, that is in the case of the delta connection, both phase voltage and the line voltage are same. Therefore, between AB, BC and CA is also 100 volts. 100 volts. Here also across AB, BC and CA is 10 volts. That is, the turns ratio as well as the line voltage ratio remains the same. Then if you are drawing the vector diagram for this is the voltage across AB, BC and CA is the sequence. That is AB, BC, CA. That is AB, then BC is 120 apart from AB, then the CA, which is lagging BC by 120 degrees. Then it is a zero phase shift between the primary and the secondary. In that case, only with a reduced ratio of voltage, that is 10:1, we have got vectors in the secondary. That is, AB is same in phase with this AB, but with reduced the magnitude because the ratio is 10:1. Then the BC then it is CA. This is a vector diagram for delta delta connection with zero phase shift, with a zero phase shift, because here both having the same thing. That is just, I will show you that also. This I am putting here. You can see here the phase shift of the neutron is 0 here. Both are having the 0 plane. Therefore, it is a 0 phase shift, the connection. Means the sequence of ABCs remains same, as well as in the primary and secondary is in phase with a ratio of 10:1. Then we have got another possible connection, that is 180-degree phase shift, that was studied in your star connection in the similar fashion. You can see here. The neutral, between the neutral, there is shift of 180 degree here. It is 180 degree. Okay. Now, if you are drawing the vector diagram for this, the primary is once again it is AB, BC, and CA. That is sequence is it is AB, BC, and CA. But here it is the secondary is shifted by 180 degree. Means AB is shifting in the secondary 180 degree. BC is also shifting 180 degree in the secondary, and CA is also shifting 180 degree. That is exactly opposite side of the primary. Just you have to look into this vector diagram. This AB with a reduced magnitude, because it is 10:1, I am considering here. Therefore, this AB is exactly opposite to this. Then the BC is exactly opposite to this that I am drawing here. That is BC. And the CA exactly opposite to this, that is 180 phase shift that I am drawing here. That is how we are getting is ABBCCA. Here the phase shift is 180 degree. It is 180 degree phase shift. What I am getting here. Some of the important points regarding the delta delta connections are the voltage. The only disadvantage of this delta delta connections is that there is no neutral, that we have discussed. This connection is useful when neither primary nor secondary requires a neutral and the voltage are low and moderate, that I discussed. Then the ratio of the secondary, the phase voltage to primary phase voltage V2P by V1P is same as its line ratio, that is PLL, that is the secondary, to VLL of the primary is V2P by V1P, that is equal to K. At the same time, the ratio of the line to line currents is IL1, that is in the delta connection primary to the line current of that should be delta, that is a delta, that should be K. That is, this is also delta here. That is the ratio of the primary current to the secondary current, because the current ratio is exactly opposite to the voltage ratio, that is IL1 by IL2 in both in the delta is root 3 I1P divided by root 3 I2P. Root 3 get cancelled, it is 1 I1P by I2P, that is also you are getting that. The transformation ratio is remains same for the turns ratio as well as line to line voltage ratio or line to line current ratio is remains the same. Some of the advantages of the delta connection, just I am summarized here. The sinusoidal voltage and the secondary voltage you are getting, because if any the third harmonic contents are present in the system because of the magnetizing current, that can be there is a path in the circulating in the delta in the primary. Therefore, we are getting the secondary voltage is sinusoidal voltage, because the whatever there is a third harmonic contents are there, that is circulating inside the delta connection of the primary. And it is also suitable for the unbalanced load. It is capable of handling the unbalanced load also. Then they carry 58% of the load if one of the transformer is faulty in the transformer band. That is, I told you, that is, even though there is one of the transformer is fails in the three-phase band, in that case the system will continue with a reduced capacity of 58%. And there is no distortion in the secondary voltage because of there is no content of the third harmonics which is present in the secondary side, because whatever there is a magnetizing, the third harmonic components are there that are circulating in the primary only. It is economical for the low voltage, that is a delta connection, because due to the delta connection, phase voltage is same as the line voltage. And because the voltage is less, it is a reduced cross section of the conductor is required. The conductor required of the smaller cross section, as the phase current is 1 by root 3 times the line current. Because if you are comparing in the delta connection, the line voltage is equal to phase voltage, whereas in the case of the line current is root 3 times the phase current. It is increases the number of turns per phase and reduces the necessary cross-sectional area of the conductor. Thus, the insulation problem is not present in the case of the delta connections. These are some of the important advantages of connecting the delta connection. In the next session, we will look into the zigzag connection of the three-phase transformer.